Good morning, dear students. Let us have a look at this question from JEE Advanced 2020. This question is from the rotation chapter. So let us first analyze the question. Put a uniform meter scale horizontally on your extended index fingers with the left one at 0 centimeter and the right one at 90 centimeter. So the left hand is at 0 centimeter and the right hand is at 90 centimeters. When you attempt to move both the fingers slowly towards the center, initially only the left finger slips with respect to the scale and the right finger does not. So initially only the left finger slips and the right finger does not. After some distance, the left finger stops and the right one starts slipping. So the left one has stopped slipping and the right one starts slipping. Then the right finger stops at a distance XR from the center of the scale. So this right finger has stopped at a distance of XR from the center of the scale. After that, what happens is, see, after the right finger stops at a distance XR, the left one starts slipping again. So this left finger which is there here, this stops at a distance XR and the left one starts slipping again. This happens because of the difference in the frictional forces on the two fingers. So he's saying that one stops, the other moves, this one stops and this moves. It is due to the difference in frictional forces on the two fingers. If the coefficients of static and dynamic friction between the finger and the scale are 0.4 and 0.32 respectively, the value of XR in centimeters is dash. So he has given us the coefficient of static and kinetic friction between the finger and the meter scale, and we need to find out what is this XR. So let us draw the free body diagram of this stick and analyze the reason as to why first this finger moves and then it stops and then this finger moves, this stops. Okay, so why this alternative movement of fingers happen, we will first analyze by drawing the free body diagram of the meter scale. So let us first draw the free body diagram of the meter scale. Initially this left finger, this is the left finger and this one is the right finger. This left finger is at 0 centimeter mark and this right finger is at the 90 centimeter mark, which means from this end it is 10 centimeters. Now we try to slowly move both the fingers towards the center and initially only the left finger starts moving. Okay, so the left finger has moved from here to here and then it stops. And after this stops, the right finger starts moving in this direction. Now this right finger has moved in this direction and stopped here. It has stopped at a distance of XR from the center. And once it stops here, this left one again starts moving. So what we need to find is, what is this XR here? Next, let us move on to analyzing the normal reaction forces that the fingers exert on the rod. So these two fingers, the left finger and the right finger, they exert a normal reaction on the rod in the upward direction. This you see here is mg. So let us analyze these normal reaction forces as these are moving towards the center. So as this rod is in translational equilibrium, okay, it is in translational equilibrium, we can write the net force on the rod as 0. So we can write N1 plus N2 minus mg equals to 0. So N1 plus N2 minus mg equals to 0. So this is the first equation. Next, this rod is also in rotational equilibrium. So what we'll do is we'll write the torque about O. Okay, so this is the center of the rod. We'll write the torque about O, and this torque about O must be 0 as the rod is not rotating. So due to mg, the torque will be 0. Due to n1, okay, the torque will be n1 into x1. Due to n2, n2 into x2 equals to 0. So n1 x1 minus n2 x2 equal to 0. This equation, okay, this equation can be written as n1 by n2 equals to x2 divided by x1. At this instant, as x1 is greater than x2, so n2 is greater than n1. So as x1, this is greater than x2, so n2 is greater than n1 from this equation. We come to a very important conclusion here, that is the finger nearer to the center exerts higher normal reaction force on the rod. So you see that this finger is nearer to the center than this, so this will exert more normal reaction force on the rod than this. But one more important point is that the sum of these two must remain constant. See, the sum of these two must be mg, but whichever is more near will be the greater force between these two. Let us now move the fingers and see how the magnitudes of these normal reaction forces are changing. So when this finger has come from here to here, the normal reaction N1 has increased and N2 has decreased. Now as the right finger has come towards left, okay, as the right finger has come from here to here, the normal reaction, this one has decreased and this one has increased. I will play the schematic once again, and one more thing I want you to observe. When x1 is equal to x2, okay, when both are at equal distances from the center, when these both fingers are at equal distances from the center, n1 is equal to n2. So I'll play it once more, you just observe it, okay. Let us analyze the friction force on the rod due to the fingers. As the fingers here are moving towards the center, see, let us take the left finger. Left finger is moving in this direction, okay. So the friction on this finger will be towards in this direction, towards the left, okay. So the friction on the scale will be towards right. Similarly, this finger is moving in this direction and the friction on this finger will be towards right, and due to this finger on the rod will be towards left. So the friction due to both these fingers on the rod will point towards the center. Let us now analyze why the left finger moves initially and right finger remains at rest. Let me take some values so that it will be easy for you to understand. So we have discussed that N1 is lesser than N2, okay, and I will just take N1 as 1 Newton, okay, and N2 as 2 Newton. Just some random values we are taking so that you can understand why the left finger moves initially. So Fs max, the maximum value of static friction here will be mu s times N1. So this will be 0.4 Newton, okay. And the kinetic friction, the value of kinetic friction here will be mu k times N1, which is 0.32 Newton. Similarly, on this finger, the right finger, Fs max, the static friction maximum value is mu s times N2, that is 0.4 times 2, which is 0.8. And the kinetic friction value will be mu k times N2, which will be 0.64. Now let us say you have placed your finger here and here. Okay, you have placed your finger here and here, and you are not moving the fingers. You are not trying to move your fingers towards the center. So what will happen? The normal reaction force will be acting, and as you are not trying to move them towards the center, there will be no frictional force here. The frictional force will be 0. Now apply a little effort with your fingers to move them towards the center. So both fingers, you are applying the same effort to move towards the center, and say it is 0.1 Newton. Okay, you have applied a 0.1 Newton force. Now what happens is, as Fs max here is 0.4, considering the left finger, the Fs max is 0.4 and you have applied a 0.1 Newton, so this left finger will not move. Okay, coming to the right finger, you have applied 0.1 Newton here. The maximum value of static friction is 0.8 and this will also not move. Next, say you increase the force on your fingers to 0.3 Newton, which means you are trying to move your fingers towards the center with 0.3 Newton. So coming to the left finger, you are applying a force on the left finger 0.3 Newton and trying to move it. So what happens, as the Fs max is 0.4, the left finger does not move. Coming to the right finger, you are applying 0.3 Newton and the static friction maximum value is 0.8 Newton. Even this finger does not move. Next, you increase that force to 0.41 Newton. Okay, you increase the force which you are applying by these two fingers to 0.41 Newton. Now see, for the left finger, on the left finger a 0.41 Newton is being applied and the static friction maximum value is 0.4. So what would happen here, tell me? This finger will start to move towards the right. I mean, it will be moving towards the center. It will start to move towards the center now. Okay. The right finger also you are applying 0.41 Newton. Okay. You are applying 0.41 Newton here and maximum static friction value is 0.8 Newton. Okay. So this finger will not move now. As and when you apply 0.4 Newton, a little greater than 0.4 Newton, this is at rest, this right finger is at rest and the left finger starts moving. So I hope you have understood why initially the left finger starts moving towards the center and the right finger is at rest. So in the last part we have seen that the left finger starts moving and the right one is at rest. Now let us analyze what happens while this left finger moves and the right one remains at rest. Okay, so as this left finger is moving in this direction, how these forces are changing, how N1 is changing, how F1 is changing, how N2 is changing and how F2 is changing, we will see. The reason we have to analyze this is for the next part of the question. The next part of the question is what? The left finger comes to rest and the right one starts moving. So that is the next part of the question, right? So to answer that, we need to analyze what happens during this process when this finger moves and this is at rest. As the left finger moves to the center, N1 starts increasing and N2 starts decreasing. We have already discussed this, so let us have a look at the schematic here. As left finger slips, kinetic friction acts on the scale and the value of this kinetic friction equals to mu k into N1. Now we have observed here that as this left finger slips this side, N1 is increasing, right? So if N1 increases, this kinetic friction is also increasing. So as N1 increases, the kinetic friction Fk1 also increases. Let us now see what is happening at the right finger. When this finger was moving left now, at the right finger what is happening is, as right finger is at rest, static friction acts on it. So there is a static friction which acts on the right finger because it is at rest. And we saw that this rod here is in equilibrium. So these two frictions must be equal always. So the kinetic friction must be equal to the static friction on this. So as this kinetic friction is going on increasing, the value of this static friction is also going on increasing. It has not reached its maximum value, but the static friction is also going on increasing. So let us have a look at the schematic once again. I want you to observe the friction here, the frictional force I want you to observe, okay, when I'm playing the schematic. Let us move on to the next part. Now what he says is, after some distance, this left finger stops and the right finger starts moving. So let us look at why does the left finger stop and the right finger start moving. We have already seen this in the previous part, that as fk1 is increasing because n1 is increasing and fk1 equals to fs2. So just remember this, okay, right now. Let us look at the right finger. As n2 is decreasing, so we have seen that n2 is decreasing, the maximum value of static friction also decreases. The maximum value of static friction that acts here, that also decreases as fs2 max is mu s into n2. So n2 is decreasing, this is also decreasing, okay. Now we come to a very important point. When fk1 equals to fs2 max, the left finger stops. Let me help you understand this statement, okay. Let us take some random values. Now we know that the kinetic friction here is going on increasing as this finger is moving towards center. So initially let us say this kinetic friction is 1 Newton. Here the static friction is also 1 Newton. Next, as we know kinetic friction is increasing, next it is 2 Newton, okay. It is 2 Newton. Here also static friction becomes 2 Newton. After this, let us say we are increasing it to 3 Newton here, okay, we are increasing it to 3 Newton, and at this instant, the maximum static friction is below 3 Newton here, okay. The maximum static friction is below 3 Newton. What happens is, the friction on this finger, is more or just becomes more than the friction on this finger, okay. The friction on the left finger becomes just a little more than the friction on the right finger. So when you're applying the same force on both these fingers, what happens at this instant is, this finger stops and this starts to move, okay. This finger stops and this starts to move. So we have come to a very important part of the question here. Let us now calculate where does the left finger stop. So this left finger is there here, right? So where does it stop? So let us say the left finger stops at xl from the center. So this distance here from here to here is xl, and the left finger stops here. So we have discussed this condition that fk1 equals to fs2 max. So fk1 is mu k times n1. So this friction force equals to mu k times n1, and fs2 max is mu s times n2. This fs2 maximum value is mu s times n2. So this is the first equation. Next, as the scale is in rotational equilibrium, we can write the torque about O at this instant. So O is the center. We can write the torque about this at this instant, and it must be 0. Or we can say the torque due to N1 must be balanced by the torque due to N2. Okay. The frictions, the contribution to torque due to these frictions will be 0. Okay. So there will be torque only due to N1 and N2. So we can write torque due to N1 as N into XL. Okay. So N1 into XL equals to N2 into 40 centimeters. See, he has given this as 10 centimeters. So from center to here will be 40 centimeters. So we can say the torque due to N2 is N2 into 40. So this is our second equation. So if we solve these both equations 2 and 1, okay, so I'm dividing 2 by 1, we get XL by mu K equals to 40 by mu S. So when we solve this equation, we get XL equal to 40 times mu K by mu S. Okay. So the left finger stops at a distance of 40 times mu K by mu S from the center of the meter scale. Now let us look at where does the right finger stop. So this was the question which he had asked. Let us again look at the schematic to visualize and see what is happening. So you see left finger is moving and it stops, then again the right finger moves and again it stops here. Okay. So let us say the right finger stops at XR from the center. So this is XR and the right finger stops here. So exactly the condition we had used in the previous case we'll use now also. Okay. Which means the FS1 max when it is equal to FK2, the right finger will stop. Okay. So these N1 and N2 are changing. Okay. I have just written them as N1 and N2, but they are changing as the fingers are moving. So Fs1 max is what? Fs1 max is mu s times N1. So the coefficient of static friction into N1, and Fk2 will be mu k times N2. So mu k times N2. Let us say this is the fourth equation. Next, as the scale is in rotational equilibrium, the torque about its center we will take. So the torque about its center is 0, which means the torque due to N1 should balance the torque due to N2. So I'm writing N1 into XL. So N1 into XL must be equal to, okay, so N1 into XL must be equal to N2 into XR. So which is equal to N2 into XR. So this is our fifth equation. So dividing 5 and 4, so dividing this equation with this equation, we get XL by mu s equals to XR divided by mu k. Again the normal reaction here and here will get cancelled. So when we simplify this, we get XR equals to mu k by mu s into XL. We have already calculated what is XL, and this XL, this distance is mu k by mu s into 40. So I'm writing it here. So when we put the value of mu k and mu s here, we get XR equal to 0.32 divided by 0.4 whole square into 40. So we get the final answer as 25.6 centimeters, which means this right finger will stop at a distance of 25.6 centimeter from the center, and after this again the left finger will start moving. Okay, and then again what will happen, this left finger will stop and the right finger will start moving, and so on. Okay, and finally when you see these both fingers, they will meet at the center of mass. You can do this experiment in your home. You can also take a scale, another scale where its center of mass is not at the center but somewhere here. Okay, might be you can take a walking stick wherein the center of mass is not at the center but somewhere to the side, and do the same thing. You put your fingers one to the left and one to the right, and you start bringing those both to the center. These both fingers, they will meet at the center of mass of that walking stick. So I hope you have understood this question in full, and see you all in the next video.